All right, let's jump right in. We're going to talk about one of the most fascinating, and honestly, one of the most surprisingly effective algorithms out there in machine learning. It's called naive Bayes. Some people have even nicknamed it the idiot's Bayes, which sounds harsh, right? But as you're about to see, this thing is actually brilliant.
So, have you ever stopped to think about how your inbox just knows what's spam? I mean, a message comes in and poof, it's either in your inbox or buried in the junk folder. And most of the time, it's spookily accurate. How does it do that?
Well, it's not some crazy, complex set of rules trying to understand language the way we do. Nope, it's actually all about probability. The whole system is basically just making a really educated guess based on the words it's seen. And at the very core of this whole guessing game is a famous and actually pretty simple formula.
And that formula is Bayes' theorem. All it really is, when you boil it down, is a way to update what we believe based on new evidence. You start with a guess, you get some new info, and the theorem tells you how to adjust your guess. It's that straightforward.
Okay, so this breaks it down into plain English. That posterior, that's just our final updated belief. And how do we get there? Well, you take your prior, that's your initial hunch, and you multiply it by the likelihood of seeing the new evidence. Then you just divide by the evidence itself. It sounds a little abstract, I know, so let's make it super concrete with an example.
All right, let's say a new email comes in, and the text is just, "Dear friend." How do we decide if it's spam or not? Well, first we got to look at the data we already have. Imagine we've already gone through a ton of emails, separating them into normal and spam piles, and we've counted how often certain words show up in each pile.
But wait, before we even start looking at the words dear and friend, we need a baseline, a starting point. This is what we call our prior probability. Basically, just ask yourself, without knowing anything else, what's the general chance that any random email is spam versus normal?
And a super common way to get that number is just to look at the data we train the model on. So, for our example, let's say we had 12 messages to learn from, and 8 of them were normal. That means, right off the bat, we have about a 67% chance a message is normal and a 33% chance it's spam. That's our starting guess, our prior.
Okay, so here's the key part. We take that prior guess and we combine it with our new evidence, the words dear and friend. We're going to calculate 2 separate scores. For the normal score, we take the normal prior, that's 0.67, and multiply it by the probability of seeing dear in a normal email and by the probability of seeing friend in a normal email. Then we do the exact same thing for the spam category.
And once you crunch the numbers, bam, the result is crystal clear. The score for normal is way higher than the score for spam. So the classifier looks at that and says, yep, this is a normal message. It seems pretty simple, right? But, and this is a big but, this simplicity is only possible because of a huge assumption the model is making.
This right here is why we call it naive Bayes. The algorithm is built on this really bold and, let's be honest, almost always wrong assumption. It assumes that every single word in the message is completely independent of all the other words. It's like they have no relationship to each other at all. What does that mean exactly? Well, it means the model doesn't see a sentence with grammar and structure. It sees a bag of words, literally. Imagine taking all the words from an email, tossing them into a bag, shaking it up, and then just pulling them out one by one. The order, the context, it's all gone. It just sees a jumble of words.
So to a naive Bayes model, the phrase dear friend and the phrase friend dear are exactly the same thing. They have the same words, so they get the same score. The order means absolutely nothing. Now, we know in real language that's just not true, but the model, it's naive. It just doesn't care.
Okay, so this super simple model works surprisingly well a lot of the time. But it has one giant glaring weakness, an Achilles heel, if you will. What on earth happens when it sees a word that it's never seen before in one of the categories?
Let's take a new message. Lunch, money, money, money. Now, let's pretend that in all of our training data, the word lunch only ever showed up in normal, legit emails. It never once appeared in a spam message. So what's the probability of seeing the word lunch in a spam message? Well, based on our data, it's 0. A big fat 0.
And that is a massive problem. Remember how we're multiplying all those probabilities together to get our score? Well, what happens when you multiply anything by 0? The whole thing becomes 0. So it doesn't matter that the word money is in there 4 times, a huge red flag for spam. The single word lunch just wiped out the entire calculation. The spam score is 0. The whole model just breaks.
So, how do we fix this catastrophic failure? Thankfully, there's a really elegant little trick called Laplace smoothing. It's also known as additive smoothing, and the idea behind it is beautifully simple. We just pretend we've seen every word one more time than we actually have. We add a count of 1 to every single word in our vocabulary.
So look what happens here. Every word's count in the spam category gets a little bump. The word lunch, which used to have a count of 0, well, now it has a count of 1. And just like that, its probability is no longer 0. Problem solved.
And with that one simple move, the whole zero probability problem just vanishes. By adding this tiny little pseudo count, we make sure that one new, unexpected word can't bring the whole system crashing down. Our classifier is now robust. It can handle new words and still make a smart guess.
Now, one thing to keep in mind is that naive Bayes isn't just one single algorithm. It's more like a family of them. The one we've been using for our spam example is called multinomial naive Bayes, and it's perfect for stuff like word counts. But there are others like Gaussian and Bernoulli, and they're each built for different kinds of data.
So which one do you use? It really all comes down to what your data looks like. If you're working with continuous data, think things like height, weight, temperature, you'll want Gaussian naive Bayes. For discrete counts, like we did with counting words, multinomial is your go-to. And if your data is just a simple yes or no, like does this word appear in the document, yes or no, then you'll use Bernoulli.
And don't let its simplicity fool you. Naive Bayes is seriously powerful. We're talking way beyond just filtering your junk mail. Take a look at this. This is an interface for a medical diagnosis system. It takes in a bunch of patient data, runs it through a naive Bayes classifier, and helps predict if a person has diabetes. And get this, one study found it was 95% accurate. That's a so-called naive model making a huge, life-saving impact in the real world.
Which kind of brings us to a really interesting final thought. The entire naive Bayes classifier is built on an assumption that we know is just plain wrong, that all the words are independent. In reality, they're not, and yet the algorithm works incredibly well. So it really makes you wonder, right? If a model that's this naive can solve problems so effectively, what does that say about the problems themselves? Maybe a lot of the complex challenges we're trying to solve are actually simpler at their core than we give them credit for. It's something to think about, isn't it?